Welcome to Maths with EJD. In this video, we'll go ahead to solve some of the partial differential equations we've been talking about in previous videos. Starting from here, we'll be talking about separation of variables for the heat equation. Separation of variables for the heat equation. So separation of variables is a method that we need that can be used. Before now, we've seen the method of characteristics and numerical methods for PDEs. So separation of variables is another analytical method of solution for heat equation. So we are going to be using this to solve heat equation, wave equation, and Laplace equation. So look at the problem setup now. Problem setup. Solve the one-dimensional heat equation, partial u partial t equals alpha squared partial squared u partial x squared. So we need to take care of this, all right, using the method of separation of variables. Okay. Now, one thing that may be missing here is the initial condition. Okay, well, as we go on, we'll take a specific case with a given initial condition. So let's go for this now. So basically, we are using the method of separation of variables. So let's see how this works. So again, let's refer to the method. Method is separation of variables. Obviously, it's difficult. It may be hard to use method of characteristics for this because it is not a first order partial differential equation. So we're talking about method of separation of variables. So the idea is to assume a solution of the form u of x comma t equals x of x and t multiplied by t of t. So this is simply saying that the solution to the problem, normally because u is the dependent variable, so u is the dependent variable, right? And then t and x, so x and t, x for space and t for time, are the independent variables. Okay, so independent variables. So what method of separation of variables assumes is that the solution u x of x comma t is a product of the space component x of t and the time component t of t. That's where we have the idea of separation of variables. So that's the assumption in this situation. And if that is the case, so we are saying that we now need to, because u is this now, we can put it into the original expression. So with this now, we can then have that we have to differentiate, right? So this simply means that x of x, u of x comma t is equal to x of x multiplied by t of t. So inserting that, to substitute to substitute into the heat equation, So see the heat equation again. The heat equation says we have partial u partial t equals alpha squared partial squared u partial x squared. So this simply tells us that since u of x comma t is now x of x multiplied by t of t. So if you need partial u, partial t. If you are differentiating with respect to t, so the focus is on the t in this situation. So that means that x of x remains a constant, and then we differentiate t. So we now have dt of t dt. Okay, so that's what we need for the right-hand side. That's for this side now. Now for this other side, we need partial squared u, partial x squared. And for us to get that, first of all, we need partial u, partial x. So for partial u, partial x, if you look at what we have x of x that multiplied by t of t. So t of t will be constant now. So partial u, partial x simply tells us that we have t of t fixed, okay? And then we now have dx of x dx. That's first derivative. Second derivative, partial squared u, partial x squared. So we differentiate with respect to x again. Again, t of t remains constant, and we have d squared x of x dx squared. So this is now what we have for the other side. So putting all this, so putting this together, so carefully, we see that we have partial u, partial t equals alpha squared, partial squared u, partial x squared. So partial u, partial t is x, partial u, partial t, yeah, is x of x dt of t dt. So so I can just say that is x of x dt of t dt here. And alpha squared is partial squared u, partial x squared. That will be multiplied by t of t, then d squared big X all over d small x squared. So that is that expression right now. So, and from our knowledge of differential equations already, we can do separation of variables. So we collect terms that look alike together. So let's see how this goes. So, so collect like terms. So this whole thing, this whole thing, we can move it to this side, while x of x comes over here. And in that situation, we just have 1 over alpha squared, then 1 over t of t. That t of t now comes, and then we have the t of dt, the t of t dt, and that is equal to x of x goes to the other side. So we have 1 over x of x d squared x dx squared. So if we take this as some kind of constant that is equal to, say, equal to minus lambda. So we equate it to one particular thing. So we take it to be equal to minus lambda. So so it means we can equate this to minus lambda, and we can also equate this to minus lambda. That's why we have this minus lambda here. Okay. So now because everything is now neatly separated, we can take them separately. So let's go. Thus, you can see we get ordinary two ODEs, two ordinary differential equations, right? And now that we have that, we can then have we can have 1 over alpha squared t of t, then dt. Okay, here I can remove the of t because we already know what that is, right? So t is simply is a function of t. So 1 over alpha squared t of t dt is equal to minus alpha, minus lambda. And if that is the case, then we can multiply through. We can multiply through by alpha squared t. So that will be dt, the big T dt equals minus alpha squared lambda t, like that. So that we now have dt plus alpha squared lambda t equals 0. So this is our equation in time. So in fact, we get two of these. So the first one is the time part. This is the time part now that we are dealing with. So this is the time part. So that's the time part now. So we can keep that right now for the time part. Then we also have the space part. We have the space part. So for the space part, we simply have 1 over x. I don't want that to look like alpha. 1 over x of x d squared x dx squared equals minus lambda. So we can have d squared x dx squared equals minus lambda x of x. And that is the same thing as, so we can get rid of the of x now just for to make things easier. So we have d squared x dx squared plus lambda x equals 0. So this is the space part now. It's time and space. So we we have those two. Then to move on, let's have this and say we now have this. So solve the space part. Solve the space part. So there are two ODEs, and we already know how to solve ODEs from previous experience. So we now solve, d squared x dx squared plus lambda x equals 0 with boundary condition x of 0 equals 0 and x of L equals 0. We are talking about heat equation, right? So it's more like you have heat flowing in a rod. So heat flowing in this metal rod, the length is L. So the beginning is 0. At the end, the full length is L. So we are saying that the heat at this point, X at the beginning, the heat is 0. And at the end, the heat is also 0. So it's more like maybe heat is applied, at somewhere around here. Maybe you have a candle. Maybe you have a candle somewhere here burning, applying heat to that. So we have that boundary condition. That's the kind of idea for heat equation. So in this case, of course, we can solve using characteristic method, right? So using the characteristic equation method, you remember that for d squared x dx squared, we just get r squared plus lambda x. We just simply give us lambda, and that is equal to 0. So that means that r squared is equal to minus lambda. So that means that r is plus or minus I root lambda, basically, because that's going to be complex because of the negative sign. So with that now, we can say, so the general solution is, and when you get complex results like that, it simply means you're going to have, interestingly, the real part is 0. So it's fully rotate, fully oscillatory, yeah. So the general solution is x of x equals a, which is a constant, sine lambda x plus b cos sine square root of lambda x, rather, plus b cos root lambda x, like that. So the next thing we want to do is to apply the first initial condition, apply x. Okay, it's a boundary condition. So apply x of 0 equals 0. What it simply means is that at x, the small x equals 0, big X is also 0. So we can apply that. So if we do that, it means that, so this big X is 0. So we have 0 equals a sine root lambda times 0 plus b cos root lambda times 0, right? So this is 0 equals a sine 0 times, oh, that is 0 plus b cos 0. A sine 0 is 0. Sine 0 is 0, so 0 times a is gone. Then cos 0 is 1, okay? So it means that 0 is equal to b. So b is simply equal to 0. So b is taken care of. So if b is taken care of now, all right, the general solution, the general solution has been reduced. The general solution is now only with a, because this part is gone now. So we have x of x. So x of x is equal to a sine root lambda x. Okay, so we have that. Then now we also have to apply x of L equals 0. So apply we apply the other boundary condition, apply x of L equals 0. What this simply means is that when small x is equal to L, then big X is equal to 0. So again, that means this is 0, okay? So this is 0 equals a sine root lambda times L, okay? So we have 0 equals a sine, a sine, a sine root lambda multiplied by L, okay? Now, what this simply means, okay, with this now we can, of course, a must not be 0. Given that a is not equal to 0, so we can divide through by a. So we finally have that sine root lambda multiplied by L is equal to 0. So now this is something legitimate to deal with. So at what values do we have lambda not equal to be equal to 0, right? So this simply means that we have if you take arc sine of both sides, right? We want to get rid of sine. So we can take arc sine. So arc sine of sine square root of lambda L equals arc sine of 0. Okay, so this cancels out simply. So we have root lambda L equals arc sine of 0. Now the question now is at what values, where in what places, because sine is definitely a periodic function. So after every particular value, you come back to 0. You know, if you draw the sine curve, it starts from the origin. So it goes, comes. Uh, that's not consistent, but let's say goes, comes. So at all these points, origin 0, this is 0, this is 0. So this point now will tell us something. So, and a general representation for those points will simply be what we know as n pi. Okay. For instance, when n is 0, that's the origin. So sine 0 is 0, basically. Okay. Then when you go to 1. So pi is 180. So you see this whole movement is 180 degrees. So after every 180 degrees, we come back to 0. Okay. After another 180, we come back to 0. After 180, we come back to 0. 180, we go 0, 180, and we go like that. So generally, arc sine of 0 is n pi. For any value of n, you always get 0 for that. Now, if that is the case, then we can take care. We're actually looking for lambda, right? So generally speaking, so and this happens for, like I said already, this happens for n equals uh even if we start from 1, right? But if we start from 0, but let's go for 1, 2, 3, and so on and so forth. So in that case now, we can then say that if you take the square of both sides, or we can at first say square root of lambda is equal to n pi over the length, and then we can square. So because we have the ends now, so we can say lambda n, because that n is like the all the values that go. So we can square both sides. So we have square root of lambda n squared equals n pi all over L squared. Okay. So in that case now we just simply have lambda n, because this cancels this. So lambda n is equal to n pi over L all squared. So with that now, we can then have our x of x. So how did we start? Our x of x, when we started out, b is already gone to 0, but a has a value now. So the most recent form that was valid, you go back to it. So, and this is this one. So you have x of x equals a sine root L, I mean root lambda x, right? So if you follow that now, so we have now we have xn of x because it's not all about the n. Xn of x is now an, which we didn't get in short terms. But one thing we got out of it is, you remember, this was sine root lambda x. Okay. Now root lambda x means we now have an sine. So root lambda will now be root of whatever we got for lambda n. So that will be n pi over L all squared multiplied by x. So that will be an sine. So square root cancels root. So we just have n pi over Lx. Okay. So that is our xn of x. So for the space part, we have that result. Okay, so we can go ahead and solve for the, okay, let me move over here for this, and then I'll use this with green. All right, so solve for the time part. So we've taken care of the space part. Solve for the time part, which is t of t. So don't forget the expression we had was the expression is up here. So dt plus alpha squared lambda t equals 0. But now that we know that it's all about uh the ends, because we have an oscillation happening. So it means we now have dt plus alpha squared. Instead of just lambda, we have lambda n of t equals 0. And how do we do this? This can be dt equals minus alpha squared lambda n t, because we can do separation of variables for sure. So we have 1 over t divided through by t. 1 over t dt equals minus alpha squared lambda n. Okay. So in this case now, we can integrate both sides with respect to t. Okay, so integrate both sides. So we have integral of 1 over t dt. Okay, what should I be doing here? Yeah, instead of what I just did there, right? We are separating variables. And when we separate variables, what we do is that we carry the dt to the other side, right? So we have dt all over big T equals minus alpha squared lambda n dt. Yeah, this is what should be done. And then we can now integrate both sides. So we have integral of dt all over big T equals minus alpha squared lambda n, since we are just integrating with respect to t. Okay, so this can go. So integral of dt over t, we already know it's well established, and this is the same thing as ln of t equals minus alpha squared lambda n. Integral of dt is just simply t. Okay, so if we want to get rid of this now, we know we can say integral of ln absolute value of t equals exponent, we take care of ln. So exponent of alpha squared lambda n t. Okay, and with that now, this just cancels it. So t just comes down. So we have t. So t now will now be tn of t. In fact, since we have brought in lambda n, so this, okay, yeah, we can even do it at this point. So tn is now something that has been missing is that we should have a constant. So we should have a constant c. So now this is also plus c, right? Yeah, this is, so we have a plus c at the top. But since we are bringing tn here, so it will be e raised by minus alpha squared lambda n t plus cn, because it goes with the n also. And in that situation, we have tn of t equals e raised by minus alpha squared lambda n t plus e raised by cn. But there's something we need to remember. We already got lambda n the other time. You remember the lambda n we got before now. So this we can use it. So okay, so we can say let that recall that lambda n is equal to n pi all over L squared. Then you can now let e raised power cn, you can let e raised power c, okay, be equal to just big Cn, if you like, so that we can now say that Tn of t is equal to, you know, okay, no. This part should be multiplying because we are using indices. So this is multiplication. So that can now be Cn here, e raised power minus alpha squared into n pi over L all squared t, okay, all squared t, and that is what we have. Better still, we have Cn e raised power minus alpha squared into n pi over L squared t. So this is the time component. Okay, so we have got the space and time components now. So let's go for the general solution. So general solution will now be something like this, that by superposition, since the equation is linear, so the two equations in space and time are linear. Since the equation is linear, the general solution is u x of t equals, remember where we're coming from, right? Normally it should be x of x multiplied by t of t. So it means that u x of t should actually be the x of x we got, right? What was that x of x? So it's an sine n pi over L of x. Okay, normally, right? So we have an sine n pi over Lx, then multiplied by t of t, which is e raised power. Oh, so now that will be what? That is Cn, okay? We just got that now. Cn e raised power minus alpha squared into n pi over L all squared t. So that's what we have. But we can put everything together and say we have something like u of x comma t equals summation from n equals 1, that's from superposition now, equals, so if we put this whole thing together, let's call everything dn. So we now have dn. So we have dn sine n pi over L x e raised power minus alpha squared n pi over L squared t. Okay, so the coefficients, the coefficients dn are determined by the initial condition. So if you are given an initial condition, say u of x comma 0, u of x comma 0 is equal to f of x, which is summation from n equals 1 to infinity of dn sine n pi over Lx. Okay, so that dn now will be 2 over L integral from 0 to L f of x. So this is more like a Fourier thing. Sine n pi of all over Lx dx. So this will give us all the dn's. Now, can we take a specific situation? So where this now comes on, then we have this now. So let's take a specific instance, uh, specific example. Okay, so we want to solve this heat equation. Now solve partial u partial t equals d squared u dx squared for 0 less than x less than pi. So x lies within that, and t is greater than 0. So we have all of that. T is greater than 0. Okay, and then we have the boundary condition u of u0 of t, u of 0 comma t equals u of pi comma t, and that is equal to 0. And then we have ux of 0. So when time is 0, the space is sine 2x. Okay, here when space is 0, and when space is 0 and time is given, we have, and then when space is also pi and time t, so we have 0 like that. So with all the things we have done and with the general form of solution we have got already, we can just proceed and just do step 1 with this. Step 1 now, you just find the general form. Find the general form. Find the general form. So if you find the general form, so we know since alpha squared is equal to 1, because in the general form, right, we have an alpha squared that should be here, right? Alpha squared, but we don't have that, so alpha squared is simply equal to 1 now. So since alpha squared is 1 and L is equal to pi, how do we know L is equal to pi? Because of this now, because of this also. So since L is equal to pi, the general solution. So because we've done that before, but if you have this one on its own and you have not done everything you've done, so you have to go all the step we have done. So the general solution is u of x comma t is equal to summation from n equals 1 to infinity of dn sine nx e raised to power minus n squared t. So it's just what we got before, and apply to this specific situation because alpha squared is 1 and L is pi. Okay, that's the general solution. And in step 2 now, we apply initial condition. Apply initial condition. In fact, more like boundary condition, right? So we know that at t equals 0, we see that u of x comma 0 is actually sine 2x. Okay, so in that case now, if we do that, because t is 0, so if we put that here, so it means that this whole expression when t is equal to 0 would just have to be so that would be, so if we put that here, right, setting t to be 0, so we say we have summation from n equals 1, summation from n equals 1 to infinity of dn sine nx, okay, sine nx e raised power minus n squared 0, okay? So, and all of this is equal to sine 2x, so that we now have, e raised power 0, this will just be 1, okay? All of that is going to be 1. So we have summation from n equals 1 to infinity of dn sine nx equals sine 2x, okay? So that if we drill down, so this is more like we have d1 d1, okay, I mean, let's say d1, we take d1 to be equal to 1 and dn take that to be 0. That's the last one, and all of this is happening for n not equal to 2, okay? So in that case we can say thus u of x comma t is simply sine 2x e raised to power minus 40. So this is a specific result for the one we have, because everything it's no longer the generalized form, because we now have alpha squared given and we have the length of the rod given as pi. So here, separation of variables breaks the PD into two ODEs, solves them separately and superposes the the solutions to fit the initial condition. I think that is worth noting. In summary, right? In summary, separation of variables, separation of variables breaks the partial differential equation into two ODEs, solves them separately, okay, and superposes the solutions to fit the initial condition, to fit the initial condition. Okay. So just like what we saw in the example above. Yeah, at this point, let's take some practice questions. You want to practice with all that. So I just say following, solve the following PDEs using the separation of variables. Okay. Number one, you have partial u, partial t equals 4 partial squared u, partial x squared. So here alpha squared is 4. Okay. So u 0, comma t is equal to 0. U pi, comma t is equal to 0. So you can also see that L here is pi. So you also have u x, comma 0 is sine 2x. So that's one. Number two, you have partial u, partial t equal partial squared u, partial x squared. Alpha squared is 1 there, as you can see. So you have u 0, comma t equals 0, u 2, comma t equals 0. And then you have u x, comma 0 is x into 2 minus x. That's number two. Number three, so you can have different length domains where L is arbitrary. Um, okay, I mean let's leave that out. Yeah, let's do this. Partial u, partial t. So you see the heat equation is the same. So what just differs is the length and the alpha squared. I think that a thermal diffusivity or something. So u 0, comma t is 0. Then here now we have partial u, partial x, 1 comma t is 0. And then we also have u x, comma 0 to be x. So let me see your answers in the comment section, either on Facebook or on YouTube. Let me also know in the comment section how helpful these videos are for you. And if you want me to solve a problem or treat a topic, feel free to let me know that I may be able to find time to get around those ones. If you have subscribed, thank you. If you have not subscribed, please go ahead and do that, because there's a lot for you to learn here, and a lot more will be coming. Then do remember to also hit the notification bell so you can always get alerted each time a new video is released. And be sure to like and share so that more and more people can have access to this great content. Till I come your way again, keep doing math right. In the next video, I'll be talking about separation of variables for maybe wave equation or Laplace equation, one of the two. So watch out, you don't want to miss that at all. Bye.